So, this is the second lecture in this NPTEL lecture series on tribology. So, in the first lecture we have reviewed some of the very fundamentals of that friction and wear. So, one of the things I would like all of you to carry forward the thought that tribology is a system dependent property. Okay. So, tribology essentially a system dependent property, and that most of the elements of tribology like friction, wear and lubrication. So, this is the three pillars of tribology. So, friction is one pillar, wear is another pillar, and third pillar is lubrication. These are like surface dominated properties. Okay. What it means that friction between two matting solids are essentially governed by physico-chemical interactions between the asperities of the two matting solids. The result of this interaction leads to wear of materials, and how to prevent friction and wear? You need to use the lubricants, and these lubricants are essentially the major role of lubricants is to physically separate the asperities from the two interacting surfaces. So, this is in a nutshell that why tribology in the field of tribology one has to understand the characteristics of the surfaces and contacts. Now, let us start with some of the very basics of that, how to characterize the surfaces. Now, what you see here, this is the part of a sphere, right. Now, this sphere, it can appear to you it is a nominally flat and smooth sphere. So, when I say that nominally flat and smooth, essentially what it means that the word nominally flat means what you see with the naked eyes. Okay. But if you put the same sphere surface under the profilometer or under the microscope, what you see is as follows. What you see that these essentially nominally flat surfaces has lot of asperities which contributes to the roughness, and also there is some other terms called waviness. So, roughness and waviness, these two terms essentially constitute the surface characteristics of this nominally flat sphere. So, I repeat, you have the mean line, this mean line is what you see in the naked eyes, but if it a much lower length scale, if you go, then these nominally flat surfaces will consist of roughness and waviness. Now, the next question that should come to your mind is that if you say a surface is rough, how to quantify the surface roughness? So, the quantification of the surface roughness, there are a host of numbers, or where there are host of parameters which are widely used in the field of tribology. Among them, the most commonly used parameter is RA. RA is the average surface roughness. Now, let me define what is meant by RA. So, what you see again, the way I am tracing this line is essentially nominally flat surface. Okay. In this nominally flat surface, you will see there are a lot of peaks and valleys, right. These are the peaks and these are the valleys. Sometimes the peaks are very sharp, or sometimes the valleys can be sharp, or they can be bimodal peak, and there is lot of undulations, right. So, these will constitute the asperity. So, essentially these are called, what I have mentioned in the last lecture, this is called asperity. Now, RA values essentially is determined by 1 upon L what is L? L is the total sampling length, okay. L is the total sampling length. Integration 0 to L mod of yx dx, okay. What is yx? Yx is the profile height. So, if you take this particular point at this position x, this will defined as yx. So, you take various sampling length, profile length at many distances x within this span, within this length, sampling length L, you integrate it, you divide it, that result of integration by sampling length L. So, that will define you the average surface roughness. So, average surface roughness, as I said, by far the most widely used parameters, okay. So, any time people say that you get a machine surface, the first thing people ask that what is the RA value of the machine surface, and typically RA values of the various surfaces, the length scale which varies is some micrometer, okay. If the RA values goes to millimeter, that is extremely rough surfaces, it is not acceptable in most of the industrial applications. RA values must be in the order of micrometer scale. The second one is the root mean square, that is called RMS roughness, and that is RQ. What is RQ? RQ is the square root of 1 upon L, square root of 1 upon L, 0 to L y square x dx. So, what you see from this expression, the fundamental difference between RA and RQ is that in case of RQ, you are essentially taking the square. Once you take the square and then you take a square root, then what would happen that that the deviation, whatever the deviation of the asperity from the mean line, that is being squared. So, that means it is being magnified or amplified. So, you would be able to get even the very finer deviation that becomes magnified. So, essentially RQ value in reality captures very close to that real roughness values of any surface. So, if you are given the choice between RA and RQ, I would choose RQ value, because RQ value is captures much better the surface deviation, asperity deviation from the mean line. Now, this particular slide is important. What it does, it says that the two surfaces can have same RA values. So, this is your solid surface 1, this is your solid surface 2. So, S1 and S2, and as you can see that S1 RA value is 0.25 times A, S2 RA values is 0.25 times 0.25 times A. So, when you say A is can be any values, and the typically A values is mentioned here, okay. Now, although their surface roughness is equal, but their RQ values is quite different. In this particular case, RQ values is 0.58 times A, and this times is the RQ values of 0.37 A. So, 0.37 A and 0.58 A, certainly this surface is much more rough. So, if you follow strictly the RA values, then these two surfaces S1 and S2 may be equivalent, but in reality they are not equivalent surfaces, simply because they have a two different RQ values. Okay. Okay. So, this is another example that these three surfaces, again S1, S2, S3, these three engineering surfaces, to any layman, these three engineering surfaces must be different, right, because if you see the nature of the asperities are different. These surfaces, it is much more regular asperities, these surfaces the valleys are much deeper, these surfaces there are irregular asperities. You can see these asperities is much more high than these asperities and so on. So, by far these surfaces may appear to be much more uniform, okay. But if you quantify these surfaces on the terms of RA values, then what you see, they are like equivalent, right. 2.4 micron is almost closer to 2.5 micron, right. So, what I am trying to point out through these two slides is that RA value cannot be used in absolute scale to distinguish and differentiate between different engineering surfaces. There is a need to consider other surface roughness parameters like RQ values and other surfaces, which I will introduce you to later. So, while RA value is widely used in the community, I have already shown several, at least 5 examples where the two surfaces can have identical RA values, but they are essentially very different surfaces as far as the physical features of the asperities are concerned. Okay. So, in this perspective, one of the things that may be very relevant is that bearing area curve. Now, what is the bearing area curve? Bearing area curve essentially means that if you plot that deviation of any point on the surface from the mean line and how much deviation that particular height or that particular deviation is there on these particular surfaces along x axis. So, what I said along y axis, that relative cross sectional area of a plane passing through the measured surface, and then from the highest peak to the lowest value would encounter. So, what is the bearing area curve? Bearing area curve, the way I am stressing, that is the typical nature of the bearing area curve. So, what it means is that here along the y axis, it is the deviation of the profile of the profile on the surface from the mean line, and that is the how much percentage of the plane that passes through that deviation, that is plotted along x axis. So, if you see that higher bearing area, higher surface deviation, that is covered by a very small fraction of the area, whereas very low amount of this deviation, that will constitute more or less like 100% surfaces. This is a very important concept which is used in many cases to understand the difference between lubricants, different type of commercial lubricants. So, traditionally bearing area is defined as a measure of the relative cross sectional area of a plane. So, relative cross sectional area means, suppose this is a plane, this is a theoretically rough surface. Now, you take a plane, right, you take a different planes. So, these different planes are cutting not all the asperities, but some of the asperities at a particular heights, right. So, this is another asperities, this is a particular heights. So, you have to only consider what is the amount of material that is contained by this particular plane, which is cutting through the different asperities, and this percentage of the area of the plane which contains the materials, that is plotted along the x axis, and what is the height of the asperities, that is plotted along the y axis. And if you plot it, then theoretically it will give rise to this kind of characteristic curve. So, this is called bearing ratio curve, and through the measured area from the highest peak to the lowest value would encounter. So, highest peak is this one and lowest value is this one. Okay. So, this will give this is a very important concept which is used in lubrications. Okay. So, this is another representative surfaces. This is the 3D plot of this of the engineering surface, and as I said in the last slide, that is the surface height. So, if you go back to this plot, I am saying that this is the surface height for any plane. Let us say if you take this plane, the surface height is this one, right. So, if you put the surface height 3 micron or 2 micron, then you go particular here, then you see at least 15% of that 15% of the materials that will be under the plane passing through 2 micron height from the mean line. Now, if the surface deviation is minus 7 micron, that means, so let me just clearly clarify these things in this hypothetical thing. Okay. So, if you say this is your mean line, this dotted line is your mean line, okay, Then if you take for example, this is like your maximum, this is like 3 micron, let us put it this way. So, 3 micron you see this materials that is contained in very minimal, like it is close to 0. Now, if you go to minus 6 micron means suppose if it go there, then this is minus 6 micron. Then you say that most of the materials, all the materials minus 6 micron is 100%. But if you go to like 2 micron or 2 micron for example, then at least some part of the material that the material is here, that some part of the material, and this may be less than 10% or something that is there. So, if you go to mean line here, if you go to mean line, so essentially it is like 60% or more than 60%, because some fraction of the materials in the top part and some fraction of the materials is the bottom part. So, this is the cumulative distribution function of the surface height. You can see this is a cumulative. So, this is not a single mean or mode. So, this is a bimodal type of distribution. And what you see here, this is, and this is your bearing area curve. Bearing area curve, as I said, that is a typical characteristic feature. So, what is mentioned here, bearing area curve is the complementary to the cumulative distribution function, and the physical meaning of the bearing area curve is that it represents the material ratio when sliding at the surface at a certain height. So, what it means that suppose your bearing area curve you know, and bearing area curve, suppose if the material is sliding at this particular height, you know this much material will be in contact with this particular matting solids. Now, if this particular area is getting chucked off, like you know if it is getting lifted, then it allows the next level of materials to be in contact with the matting solids. So, this is the construction of the bearing area curve. You know you can get this all this 2D profile, and from the 2D profile you can get a bearing area curve. This is the typical AFM image. AFM stands for atomic force microscopy. So, that gives a very high resolution, like it goes to micron scale and even lower surface roughness, and from there you can find out that what is the valley roughness, what is the peak roughness, what is the mean roughness of the surface aspect ratio. Okay. Now, importance of the bearing area ratio curve, suppose if it is a RA is 308 micron and this is also 308 micron. So, in both the 308 nanometer. So, in both the cases RA values are the same, but if you consider that R peak to Rk, that is the peak roughness to the mean roughness values from the bearing area curve, this is less rough, but this is more rough. Why you see? You can see that is this more rough, you can see this is more rough. Okay. Although the same RA values are the same, but if you quantify the other roughness values, the Rpk versus Rk, then they are quite different. Okay. So, as I said before, the sliding of the asperities. So, in the sliding of the asperities, what happens? You have that local asperity junction that is forms during friction, and this asperity junction that will contribute to the wear of the materials. And this real area of contact is AR, is nothing but sigma is equal to I is equal to 1 to n AI. AI is your instantaneous cross sectional area of the asperity. So, all these asperity contacts will contribute to your real area of contact, but nominal area of contact is that AI at individual asperities. Okay. Now, comes to this contact mechanics. Now, contact mechanics, as I said in the first lecture, that Kenneth Johnson's book is the Bible of contact mechanics. So, you can very well see by Ken Johnson's book that about the contact mechanics. So, what is being shown here? This is a nominally flat surface and this is a one of the rough surface. This goes in the relative motion V, and this is pressed again P as a load, or P or W as a load. Okay. So, this you can see this is replaced by W. So, now this is your total asperity, this is your nominal asperity area capital A, and this is your individual spot, right. This spot are essentially asperity contact. This is the real area of contact. Now, these summation of all these spots like features, that will constitute your real area of contact. Now, how to find out that what is the contact radius A? So, this is, suppose if this is 2A, A is nothing but cube root of 3 W r star divided by 4 E star. So, these E star values you can find out by this formula. 1 by E star is equal to 1 minus nu 1 square by E 1 plus 1 minus nu 2 square by E 2. Okay. So, this is your E 1 nu 1 and this is your E 2 nu 2. So, E is your elastic modulus and nu is your Poisson's ratio. Poisson's ratio in most of the solids is close to 0.3. Now, if you consider, for example, E 1 is your steel ball where elastic modulus is 210 gigapascal, and E 2 is your ceramic, for example, alumina where elastic modulus is 390 gigapascal, or vice versa, like this is your alumina ball and this is your steel flat. So, in both cases you can find out that what is the effective modulus E star, and these E star values you have to apply here. Similarly, 1 by R star is equal to 1 by R 1 plus 1 by R 2. What is the R 1? R 1 is your radius of curvature of this particular asperity. For a flat surfaces, R 2 is nothing but infinity. Okay. So, if you consider these flat surfaces, the bottom surfaces, the R 2 values is infinity. So, now I have defined that A value, that is the contact radius. So, 2A is contact diameter. So, 2A is nothing but this, right, contact diameter. So, from there you can find out what is the contact pressure. Contact pressure according to the basic contact mechanics theory, P naught is equal to 3 W by 2 pi a square, or 3 by 2 multiplied by W by pi a square. W is your load and A is your contact radius. And how this pressure is distributed in the contact region? Pressure is distributed, pressure is PR, P naught is your nominal contact pressure multiplied by 1 minus R square by A square. R is the distance from the center of the contact zone and A is your contact radius. So, these are the more clearly defined what I mentioned in the last slide, that how to find out that what is the effective elastic modulus and how to find out that what is the radius, effective radius of the surfaces. And this is the case for the Hertzian contact on a perfectly elastic solid, and you can see that how Hertzian contact that pressure is kind of varying, and you can see this is the 2A values here and this is your Z, okay, and this is your traction. So, this is your elastic, perfectly elastic solid, and then second, the top one is a stationary rigid body. So, essentially the motion is here v sliding velocity, and that leads to the relative motion between the two solids. So, let me spend some time here just to show you that what is the surface normal stress around the Hertzian contact. So, why it is called Hertzian contact? All this theory whatever I have mentioned in this slide as well as this slide, a scientist called Hertz first proposed these equations, and on his name that we all know that this is called Hertzian contact. So, what you see here, for example, let me schematically explain this again. So, this is your nominally flat solid and this is the load W that is kind of pressed against the spherical ball. So, this is your 2A, right. So, that I have defined in before, and this is your contact zone. So, if you plot it, this is your center of the contact or halfway between the contact. And then what I am showing here, that under this kind of configuration, how these compressive stresses, how this surface normal stress will vary spatially. So, along x axis it is r by a is there, and again along y axis it is the stress it is plotted. So, there are two kind of stresses I have plotted here. So, if you consider not the Cartesian coordinates, so one is the cylindrical coordinates and one is the spherical coordinates. So, Cartesian, cylindrical and spherical coordinates. So, in case of spherical coordinates you have r theta. So, accordingly you can define sigma r and sigma theta. So, sigma is the radial component of the stress which is normalized with respect to P naught, and what is P naught? P naught I have already mentioned here, that is the normal contact stress. So, if you plot it, what you see here, that sigma theta by P naught, it will be going like this, okay. And sigma r, it goes from compression to tension, and as you grow along this region outside the contact zone, the stress is particularly tensile in nature. So, this is tensile force, tensile stresses, and this is the compressive stresses. Okay. So, this therefore, most of the contact zone is essentially dominated by compressive stresses. The second one, what is the subsurface stress field? Now, subsurface stresses is essentially the shear stress, that is the tau value. So, tau by P naught. Now, in the shear stress, it goes through a maxima at around 0.48 times A. So, along these directions it is Z by A is plotted. So, around 48 times A. So, that means almost half of the contact diameter, and at that depth this shear stress goes through maxima. And sigma r values, it goes like this, and sigma z value. So, in these cylindrical coordinates you have r theta z. So, then you have sigma r by P naught and sigma z by P naught, they will vary in the subsurface field in this fashion. To summarize, in last half an hour or so, I have mentioned that how surface roughness of the matting materials can be effectively quantified by RA value, RQ value, RZ values, and then other values is RK value, RP values or RVK value, surface roughness. And here also I have put the bearing area curve, which is very important, bearing area curve. And also I have mentioned that although the two surfaces, RA is certainly not an universal, should not be used as a universal surface roughness parameter, simply because RA values can be same for two engineering surfaces, but the RQ values can be quite different, or the ratio of this one of these two parameters can be very different for two surfaces having the same RA values. I have also mentioned that how to quantify stress distribution in elastic plastic contact as well as asbestos contact, whereas adhesion and deformation and coefficient of friction during running in period. That I will explain some of the things in the next lecture. Thank you.